All right, good morning or afternoon or evening, whenever you're watching this, and welcome to the video for AP Calc. We're going to start target 28. I can use the basic properties of integrals to solve integral equations and simplify expressions. All right, so basically what we're doing for this topic says working with properties of definite integrals helps you better understand the definite integral. Connecting derivatives and definite integrals sets the stage for the fundamental theorem of calculus. Now this part right here, you're going to like. The fundamental theorem of calculus, that's the shortcut for finding the area under the curve. Instead of doing the summation of infinite rectangles, we can use the fundamental theorem of calculus, and whoa, it gets like a billion times easier. And using the properties of integrals helps us make that even easier as well. All right, so let's evaluate this first. First off, let's take a look. We're finding the area under the square root of 4 minus x squared with respect to x. One of the nice things about these is its area. So if the shape happens to be the one we know, for instance, square root of 4 minus x squared, that's a semicircle. So instead of doing infinite rectangles there, I know the area of a circle I can cut in half. This is a semicircle, area 2. So this simplifies to 1/2 pi r squared when r is a radius of 2. So we simplify that, and that is 2 pi. Now as we do this, we probably want to be able to use a calculator, because on AP exam, half of it, a little bit less than half, is calculator based. So let's just double check this using a calculator. If you have a TI Inspire, this is how you do it. If you have an 84 or an 83 TI, again, you can use those. So we'll start, we'll do our integral from -2 to 2 of the square root 4 minus x squared with respect to x. You get 2 pi. Now some of you didn't get 2 pi because it doesn't have this exact capabilities. I got a CAS and a CX. Those have exact capabilities. Sometimes you don't. Then you probably got 6.283. Okay, just make sure you can estimate it out. All right, so let's look at some properties. I'm going to give you the theory here, and tomorrow in class we'll go through and we'll try the practice problems. All right, so what we got here, it says if an integral function is non-positive, the non-zero factors. So basically, summing this up, if our function is below the axis, okay, if our function is below the axis, when we calculate the integral, it's not going to be the area, it's going to be the opposite of the area because it's below, right? It's another way of denoting direction. You'll find your integral, it'll be negative, that means the area you're looking for is underneath the x-axis, it's below. So if it's below, area equals negative from a to b f of x dx. If there's some above and some below, this next slide, our integral will be the area above minus the area below, because the area below is negative, so it'll be area above minus a negative value, you're really adding them two together. All right? So here's a theorem. If you're integrating a constant, now you know a constant will be a straight line. So a constant integrated from a to b. Well, what shape did this make? I hope you all said rectangle, because that's a rectangle. So when integrating a constant, you're basically finding the area of a rectangle that is c high, or whatever your constant is, and then subtract your integrands, your limits of your integrand, and that's the width. So it's c times whatever b minus a is. So anytime you're taking the integral of a constant, you're just looking for the area of a rectangle that is the constant high times the subtraction of the limits. All right? Now here's some properties of the limits. We're going to get through these, practice them tomorrow. They'll make a lot of things a lot easier. For instance, what happens if I switch the limits? All right, take a look. This is like saying we have a function from b to a. Well, what if I switch limits and go from a to b? What happens when I go backwards? All right? How do we denote in calculus going backwards? Well, we do that with this little negative sign. So if we switch the limits, or switch the location of the limits, just switch them around, that's the same thing as having not switched them around and just doing a negative. So when you switch the limits, you negate your integral because you're going backwards. All right, here's some other helpful ones. All right, this first one, that's the one we just did. You switch the order of the limits. You'll just negate because you're switching directions. Now, if your limits are the same, basically what you're saying is you want to find the area under a rectangle that has no width. Well, if there's no width, the area, there's no area. If there's a constant, this constant multiple, this one's pretty easy. The constants you can just pull out. Do it without the constant, get your answer, and multiply the answer by the constant. Sum and difference, we've kind of been doing this one intuitively. Just do them separately. Because each time we've done the antiderivative of like x squared plus x, we did the antiderivative of x squared, we did the antiderivative of x, and did them separately. Okay? It's the same thing as if it's a definite integral with those limits. You do this one separately and then that one separately. All right? Now 5. 5 is a big one. 5 is one that could be very useful. What 5 is saying is we have a function. Find the area from a to b of the function. Right? You find the area of b to c. Well, why go from a to b and then from b to c when you can just go from a to c? As long as these match up like this, you can do that. And it doesn't matter if the numbers are in order. Like if this was 1, and that was 5, and this was 2, it still works. Because if you go from 1 to 5, and then 5 to 2, the 5 to 2 is backwards, and it's going to subtract off the total and give you from 1 to 2. 6 and 7 we don't use a whole lot. 6 is just the extreme value theorem. It says if the max of f and minimum f are maximum values, then the minimum, so you take the smallest value, multiply by the gap, and the largest value and multiply by the gap, that the actual value is going to be between them. So to kind of illustrate that, right? So we got a graph of a function from A to B. The minimum value is right here. Well, there's the minimum times the gap. That's the smallest rectangle here. And here's the maximum value. There's the maximum rectangle. And you can see the actual value is going to be above the minimum and below the maximum, kind of this part inside there. So that's what that's saying, except that you can find, you know, a minimum and a max, and your actual value is going to be in between. And then as far as number 7, we don't use that at all. That's more Calc 2, Calc 3 stuff. So I'm not going to worry too much about that one. All right, now here we get the practice problems. So I'm going to stop and we'll do those in class tomorrow. So those are the theories. Take a look at those, know those. And tomorrow in class, we're going to do practice problems.